This week we're going to be talking about evaluating exponential functions, identifying and graphing exponential functions. What is an exponential function? An exponential functions are one of most important functions in mathematics. Exponential functions have many scientific applications such as population growth and radioactive decay. Exponential functions are also used in finance, so if you have a credit card, bank account, car loan, or home loan, it is important to understand exponential functions and how they work. Exponential functions are functions where the variable x is in the exponent. Some examples of exponential functions are f of x equals 2 to the x, f of x equals 5 to the x minus 2, f of x equals 9 raised to the 2x plus 1 power. In each of the three examples, the variable x is in the exponent, which makes each of the examples an exponential function. An exponential function is a function of the form f of x equals b to the x power, or y is equal to b to the x power. B is called the base, and x is your exponent. The graph of an exponential function looks like the graph below. To begin graphing exponential functions, we will start with two examples. We will graph the two exponential functions by making a table of values and plotting the points. After graphing the first two examples, we will take a look at the similarities and differences between the two graphs. Now, when you start graphing exponential functions, doing a table is a great thing to do. I would use a few negative numbers. I would use a few positive numbers. Now, let's review negative exponents, okay? So, for example, if I asked you to find two, if this is my function that I'm going to use f of x equals 2 to the x. Now, if I asked you to find 2 to the negative second power, a lot of students, they wouldn't remember how to do negative exponents. But remember, 2 to the negative second power is the same thing as 1 over 2 to the second power. So that would be 1/4. 2 to the negative 1 power is the same thing as 1 over 2 to the first, which is 1 over 2. 2 to the 0, remember anything raised to the 0 power is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. So if I wanted to graph this thing, at negative 2, it's at 1/4. At negative 1, it's at 1/2. At 0, it's at 1. At 1, it is at 2. At 2, it is at 4. And at 3, it's at 8. So this is what an exponential function looks like. Okay. Now, if I asked you to graph the function y 1 to the half to the x power, okay, well, again, being able to do negative exponents is a key to these types of problems. Okay, so if I asked you to do 1/2 to the negative second, remember, a negative exponent just flips this over. So this is just going to be 2 over 1 to the second power, which is 4. So if I wanted to graph negative 2, it would be at 4. If I did 1/2 to the negative 1 power, that's just going to be 2 to the first power, which is 2. So negative 1, I'd have 2. And so on and so forth. You can just take a look at the list there. But making a table of values is a great way to graph exponential functions. But make sure you do some positive and some negative values, because it's going to help. Now, I want you to notice the difference between the two graphs. One graph is coming down. This is called exponential decay. Talk a little bit more about that later. And the one that goes up is called exponential growth. Okay, I'm going to use my marker. What's the difference? The base. If you take a look at the base of the exponent, if the base is greater than 1, it's exponential growth. If the base is less than 1, well, I shouldn't say less than 1 because negative is less than 1, but that's not the case. If it's between 0 and 1, it's exponential decay, like 1/2, 1/4, 1/3. All of those would be exponential decay. Okay, so my base is 1/2. It's less than 1, greater than 0, so it's exponential decay. Exponential growth or exponential decay. If we are given an exponential function asked to predict if the resulting graph would be exponential growth or exponential decay, all we have to do is look at the base. So for example, in this problem here, 4/3. Now some people are going to say, oh, that's decay. No, it's not. 4/3 is greater than 1. This is going to be an exponential growth function. 6/5. This is exponential growth also, because that's 1 1/5, right? So these are both exponential growth problems because the base is more than 1. Okay. Now, if I gave you f of x equals 1/2 to the x, this would be decay because it's less than 1. The graph of an exponential function, choose several values of x, and then plot the points. So in this graph here, y is equal to 2 to the x power. Base is 2, so I know it's going to be exponential growth. I know the function is going to go up. So I plot a few points, and there's my graph. If I have now, this is the base. The base is the number that the exponent goes to, right? So some people, they look at this number and say, oh, it's exponential decay. No, this is the base. The base tells me if it's going to go up or down. So I know this is going to be exponential growth because the base is greater than 1. Then what does the number out in front do? Well, kind of just makes the number. So you always do exponents first. So let's say I did -1. I plugged -1 in here. So I've got 0.5 times 2 to -1. We always do the exponent first. So that's 0.5, and that's going to end up being 1/2, right? So really, I have 1/2 times 1/2, which is 1/4 or 0.25. So you just multiply that number at the end. Now, I will tell you that this really tells you where it's going. When it crosses the y-axis, this is the number that it's going to cross at, okay? Because when you put 0 in here, 2 to the 0 is 1, 0.5 times 1 is 0.5. So it's going to cross at 0.5. So that number right there basically helps me. And when we get into problems, it basically is the original amount. What is the amount at when x equals 0? So we always call that number in front the original amount. Where does it start when x equals 0? So in this problem, I know right away that it's going to be exponential growth. And I also know that it's going to cross the x-axis at 5. So then let's take a few points. Let's take -2. So this is going to be 5 times 2 to the -2nd power. That's 5 times 1/4, which is 5/4. Okay. So at -2, this problem's at 1 1/4, right? 1 1/4. At 1, if I put it 1 there, it'd be 5/2 or 2.5. So it's going to be, oops, 2.5. So that would be right above there. Cross that 5. I put 1 in there. That's 2 to the 1st is 2. 5 times 2 is 10. So at 1, it's going to be way, ooh, this function is really going to go up fast. Like that. Just taking a few points. Now, what if I asked you to write an equation for an exponential function? Okay, so what do I need? I need the a value. Where does it start? Well, that's pretty easy to find. That's where it crosses the x-axis. So in this problem, it's going to be 2 times, and then how do I find my base? Well, my base is how fast it's going up, isn't it? So if you just take 2 points next to each other, so this point is 6, this point is 2, is that right? And if I just, I think, I'm just winging this, I think my base is going to be 3 to the x power. Okay, let's see if it works. So if I put 0 in here, okay, 3 to the 0 is 1, 2 times 1, so that works. Boom. Then if I put 1 in here, 3 times 1, or 3 to the 1st is 3 times 2 is 6. Well, that works. If I put 2 in here, 3 to the 2nd is 9 times 2 is 18. That works. So in order to find my exponent, or how fast it's going up, my base, I just have to take 2 points and divide them. Now, this way I go from left to right. Here I'm going down, so let's see here. This point here is 8. This point here is 4. So I'm going to do 4 over 8. Why am I doing 4 over 8? Because I know it's going to be less than 1, right? Because it's coming down. So that's going to be 1/2. So where does it cross the x-axis? Crosses that, or I'm sorry, the y-axis, cross it too. So my equation, I would go 2 times 1/2 to the x power. See if it works. So if I put 0 in here, crosses that too. What if I put -1 in here? Well, -1, 1/2 to the -1 power is 2. 2 times 2 is 4. Holy cow, this works. So being able to write an equation for an exponential function, not very difficult at all. All right, then we go on to exponential growth. Exponential growth occurs when a quantity increases by the same rate, that's our value, we call it, the rate in each period t. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. So here's my formula that we're going to use when we're doing exponential growth. Y is equal to a1 plus r to the t power. Now, why is it 1 plus? Because remember, we said that when it's exponential growth, it's always going to be greater than 1. So 1 plus the rate is always going to give you a value greater than 1. So let's try and come up with an equation. It says a function f of x equals 500, 1.035x models the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? Now, I could have asked you how much money was in the account at time 0. You should have said, there was $500 in the account, because this is the original amount. I could ask you what the rate is. Well, the rate would be 1 plus 0.0, so it'd be 0.035. So that would be 3.5% if we change it to a percent, because we changed the decimal point. So looking at an equation, you can tell a lot about the problem. The original amount, what the rate is going to be. Now, if I wanted to find 6, I just plug 6 in here. And I don't have my calculator, so I can't do this. So it's going to be 1.035 to the 6th power. Just plug it in to your calculator. You should get the answer out. In this problem, the original amount, it says a function where x is the time in years, models the population of a city. What will the population be in 7 years? Okay, now a question I could ask is the population going to be more or less than it started? What was the original amount of the population? Well, the original amount, 200,000 at time 0, which we don't know. I mean, it could be the year 2022. So 200,000. Now, this city's population is decreasing. Why do I know that? This is less than 1. It's decreasing. So in 7 years, my answer is going to probably be, 190 some thousand. I don't know. Just put 7 in there and you can figure it out. But I know it's going to be less than 200,000 because it's decreasing. The population of this city is decreasing since the base is less than 1. The function f of x equals 10, 2 to the x models an insect population after x weeks. To the nearest whole number, what will the population be after 4 weeks? Now, I can tell you that there were 10 in to start with, and then 2 to the 4th power. I guess I can do this one because I really don't need a calculator to do this one, because 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is going to be 16 times 10, which is 160. So after 4 weeks, there's going to be 160 insects. Now this one, it says the original value of a painting is $9,000, and the value increases by 7% each year. Write an exponential growth function to model this situation. Pretty easy. 9,000 is my starting place. It's increasing, so it's 1 plus 0.07, right? 7%. Move the decimal 2 places over, so that's 0.07. So this is going to be 1.07 to the x power. Now, then find the painting's value in 15 years. So I plug 15 in here, and I'd come up with my value. Okay. Now, exponential decay, the function for exponential decay is going to, if you take a look at the formula, it's 1 minus r. Doesn't that make sense? If exponential growth was 1 plus r, exponential decay is 1 minus r. So if they ask me to come up with some functions for this one, so for example, it says the population of town is decreasing at a rate of 3% per year. In 2000, there were 1,700 people. Write an exponential function for this. Okay, so, oops, don't know why I did that. So I've got my original value times 1 minus 0.03 to the x power. So this would really be written as 0.97 to the x power. And then if I wanted to find the population in 2012, I just plug 12 in here, because 2000 was the time I wrote this equation, so that's when x is 0. So if I want to know what the population is in 2012, I would just plug 12 in here. Do not put 2012 in there. Your answer is going to be way off. So that is exponential growth and decay. I love this stuff. It's pretty cool. You guys have a great week. Hope to see you on Monday. Bye.